Okay, our last presenter is Dimitri. Dimitri is Associate Professor at Missouri Science and Technology. He's active in ACI 237, 238, 309, S801, and SYPAC. His expertise is in rheology and placement of flowable concrete. And he's going to be providing an overview of research on reducing pumping pressure for high strength SCC. Take it away, Dimitri.
All right, thank you, Matt. What I want to give here is actually an overview of some research we did, and those who know me, back when I was in Sherbrooke, so that's a while ago. But some research we did on pumping of high-strength SCC and mixtures that are being close to SCC, and with this partner was Kamal on this project. I don't think it's necessary to introduce the what, the if, the why, and so on, but maybe the how we did this. So doing scientific research on pumping, there's only one way to do it, just to pump concrete. And what you see here is a schematic presentation of our lab scale pump circuit. So we got a concrete pump that we built in the building, then we connected pipes to it. And we got one straight section of pipes going from the right of the screen to the left of the screen that were 4-inch in diameter. And the distance between the two red dots, and the red dots were pressure sensors and our strain gauges, is approximately, give or take a couple, approximately 30 feet. And then we loop back, but we increase the pipe diameter. So instead of having 4-inch pipes, now we got 5-inch pipes. We go all the way back. Again, we get the same distance between our pressure sensors, and then everything loops back into the hopper of the pump. So we're actually recirculating concrete several times. That's just to make sure that we didn't need 17 trucks of concrete for one day. So just to show the pictures, what you see on the right is the back of the pump sitting in a building. And then the concrete actually comes here on the left from the hopper, goes through the pump system, goes in through the 4-inch pipes, turns around, goes through the 5-inch pipes. And what you see over here right there is the pressure sensor, one of the pressure sensors is being attached to it. And then it gets pumped back into the hopper, so again, to circulate our concrete around. Our testing schedule, so we pumped three different concrete mix designs in a single day. Were long days. And what we did, concrete comes from a ready-mix company, gets delivered, and we adjust the concrete to the desired consistency level. So we had already some of the high-range water using agent added in the plant, but we fine-tuned it on site. Then we took a sample of the concrete to evaluate the non-pumped fresh concrete properties, and I'll go through the list in the next slide. And then during that event, we inserted the concrete in the pipes, taking all precautions necessary, and we pumped the concrete the first time. And how do we pump? Well, we pump at different flow rates in descending order. So we go from a relatively high but still safe flow rate, because again, we're inside the building. And we decreased in somewhere between 5 and 8 different levels. And we maintained each flow rate for about 5 strokes or 45 seconds, whichever came first. At the same time, we get a pressure registration with a pressure sensor, so we can have a pressure loss flow rate relationship and really get our scientific mind around this. After we've done this, each time we take a sample of the concrete, the concrete, to evaluate its fresh properties again. So in this way, we could actually monitor the fresh properties of the concrete as well, and use them, and I'll show you an equation, and use them in the equation to actually predict pumping pressures. We repeated that 3 to 4 more times. So we got 4 to 5 different flow or different curves for each concrete, each with approximately half-an-hour interval. So we went pretty long in time. And at the end, we had another evaluation of the concrete that was kept aside just to see how that one evolved as a function of time. And then at the end, yes, we had to clean. To evaluate the fresh properties, this is what we did. I'm not going to discuss everything in detail, but what's really important for the presentation is that we measured rheology of the concrete itself. And that means we get the yield stress in the plastic viscosity, and we're not adventuring in any nonlinearity. That's what Walt was alluding to with those extremely sticky concretes. Then Brett gave a quick introduction into the lubrication layer. So we measure that separately with what we call an interface rheometer. And we get separate properties of that, but we view the properties of the lubrication layer. And then the only other one to really care about in this presentation is the slump flow or the slump, because we use that for the classification of our concrete. During that, let's say it was about a 2-month period, we did all this work in Canada in the winter. Good, we were inside, but we had 3 conventional fabricated concrete mixtures that were the product of the ready-mix company. So we didn't really play with the mix design. Now there were changes in between those three mixtures just by changing the high-range water-reducing agent content. And the strength of those concretes was approximately 7,000 psi. And then we had our own mix designs, 18 self-consolidating, and then 4 mixtures that were not yet SCC, but they were a little too flowable to be conventional. The slump flows range between 16 and 32 inches at arrival and after adjustment. And their strengths were, for most of them, around 10,000 psi, and for a couple of them, we tried to push it as high as we could with the materials we had, and we arrived somewhere between 4 and 15,000 psi. What did we all change? We changed the high-range water-reducing agent dosage on these mixtures. Some of them we changed the binder system, and I have to mention that our reference system is already a blended type 1 cement with 8% silica fume. So that's our reference. So we already have silica fume in those mixtures. Changed the water to cement ratio, changed the paste volume, and changed the aggregate gradations, but not to an extreme extent. Now on classification, and that will be important, as soon as the slump flow is below 400 millimeter, which is your 16 inches, we call this thing conventional vibrated concrete and rather going to characterize slump instead of slump flow. If the slump flow is above 24 inches, we classify it as SEC. Now, what we do here is actually take the slump flow into consideration the moment we took the sample. So some mixtures that started as SEC ended up as a highly workable concrete because it ended up somewhere between the 16 and 24 inches. And even some transitions all the way to conventional vibrated concrete because they lost so much slump. So just to give you that indication, because some data points will appear as CVC and they appear out of nowhere. But just to give that. I work in academia. And there's one thing we like to do in academia is to show equations. Now, don't worry, I'm only going to show you one. That's the one that's going to be. And this is one of the 2 equations developed by the Nicolas in the early 2000s to actually predict pumping pressure. We just slightly modified it to get some information in there. And there's a bunch of parameters that play a role, right? What you see on the left is the prediction of pressure. Depends on the length, depends on the radius, depends on the flow rate. And then you get an additional term on the right. It's one that I added because it was not included in Kaplan's equation, is rho GH, is hydrostatic pressure. And on the right side, you see all the concrete properties that are affecting that relationship. All right, let's go through them one by one and really see what's going on, right? And the question is, how can we reduce pumping pressure? Now, let's first look completely at the right-hand side of that equation. What can we play with? Rho GH. Well, G, not really. You know, we're not yet pumping on Mars. We're not yet pumping on the moon. We're not pumping on Jupiter. So G is a constant. We can't really play with that. H, well, you know, if you want to construct and put concrete on the 75th floor, not really an option. It has to go that high, right? So H is not really something we can play with. So what's left is rho. Yes, we can reduce density. That's an option. But then, I don't know who had mentioned it. I think it was Eamon, not sure. But lightweight concrete, you have a bunch of concerns with that on itself. So let's say that that's not really an option. So hydrostatic pressure is something we're going to have to take into consideration, but it's not something we can actively reduce. There's nothing we can do with that. All right, let's look into a second parameter. What about the length of the pipe? And there's the issue. We need to get the concrete to the right floor. So again, if you need to go to the 75th floor, you're going to have to, you need the appropriate length, and you're going to need that length in there. So you can't really play with this. The only thing you can potentially play with, and Eamon quickly introduced it by his nomograms, is the equivalent length. And that's to reduce as much as possible any benzo reducers in the system. But other than that, can't really play with length, right? So what we did, knowing this, what we're going to do from now on, I'll actually put the length, instead of the right-hand side, I'll put it on the left-hand side of the equation, and we'll look at pressure loss per unit of length. So that's the change in the equation, and I just added the delta to include that this is actually a change in pressure per unit of length. What else can we play with? Well, we can play with the flow rate. We can play with Q, and that works. Just to give an example, one of our concrete mixtures, sometime it was tested, you get the pressure loss, the amount of pressure per unit of length, as a function of the flow rate. And in this case, we pumped somewhere, well, I'd say up to, quick calculation, 70 cubic yards per hour. That's about the far right we got. So all these data points, we can approximate this as linear. If the concrete is nonlinear, rheologically, it will become nonlinear, but we'll neglect this in this case. So it means changing the flow rate, reducing the flow rate is an efficient tool to reduce your pumping pressure. But is that wanted, right? Do we want to reduce the pumping flow rate, and do we want to reduce construction speed? And then I'll refer to Jack's presentation. And what Donald Trump said is speed, it matters. So I can't see you and I can't hear you, but can hear you think that that is not an option. So forget Q. Not going to happen, right? We want to be as efficient as possible. So there's not a lot left. So what if you play with the rheology or the interface rheology of the mixture? And the first thing I got to tell you is that interface yield stress, so the yield stress of the lubrication layer, is too small to matter. That for the flowable concretes, I'm not saying for a stiff 4-inch concrete, it will matter in the equation, but for a flowable, close to self-consolidating concrete, it does not matter at all. It's way too small to count towards the units we have, the magnitude of pressures we have. So that one disappears. Now, what about the yield stress of the concrete? Or what about the slump flow or the slump of the concrete? Well, that one is not too small to neglect. It is there. And what we did is actually look at the pressure loss per unit of length. And we picked it, we interpolated to have our flow rate or to have our pressure loss at a flow rate of 8 liters per second, which is about 37 yards per hour. And this graph only has the 4-inch diameter pipes. So each test, you get one data point, and this is all our data points. Where the green points are SCCs, our purple points are highly workable concretes, and the black points are our conventional vibrated concretes. And the first thing you can see, because I drew a line, is there's a pretty nice correlation for those conventional vibrated concrete mixtures, right? But you got to remember, we got these mixtures delivered. It was 3 times the same mix design, and the only thing we changed was the amount of super. So yes, there's an influence, but it's not that big. It's not that huge. Well, not that huge. Okay, yes, there's about the factor 2 difference in pressure between and here, but it does not explain why these points are over here. That's the first thing. The second thing, I get 3 other points which are classified as conventional vibrated concrete. And these are points that were initially SCC or something close to SCC that lost a lot of workability. And they no longer fit the line. Why? Because something else changed. The mix design of these mixtures over here and the ones here fitting the used to fit the line, they're not the same. They're different. So there's another parameter that, you know, in here between this and this point, it's about the factor 5 difference, right? So yield stress on itself cannot explain everything. And that's completely in line with what Walt said. You know, yes, can we add more super? Yeah, but it's not really going to help you. And I'm not even just discussing segregation issues. When I'm even not discussing stability issues. It really does not help that much. It helps a little bit, but once the mixture is flowable enough, it's not really having an effect, right? So just to give the other indication, so this is the different pressure loss versus flow rate curves for all the mixtures we had, or the mixtures we had with constant compositions in here. And we go from a initial slump flow of 16.5 inches going all the way to 31 for all these curves. But what you can see is this distinction over here. And if you look at purple, black, green, red, and yellow, then more or less it's the same spot. So this is all our SCC over here. And if the mix design is the same and the only thing we change is the amount of superplasticizer, there's not a whole lot of difference. So yes, it helps. But once you get to the SCC range, there's not any help anymore from reducing the yield stress or from increasing the slump flow. So to put that in the equation, it plays a role, but just a minor role. It's nothing really spectacular for us to work with. So what's left? Well, what's left is viscosity, or the viscous constant, right? So you look at the viscosity of the concrete, or you look at the viscous constant of the lubrication layer. And these two are somewhat related. They're not completely related, but they're somewhat related. So I only show one. I only show the viscosity of the concrete. I will not show the viscous constant of the lubrication layer, but we've seen very similar effects. So we're doing the same plot as pressure loss as a function of plastic viscosity instead of yield stress at that same flow rate of 8 liters per second, and for all our 10-inch, all 4-inch pipes we had. And what you see here is that independent of all the concrete we used, this is a very good correlation. For a concrete scientist, see something with an R squared larger than 0.9, it's hallelujah, right? That's something spectacular, right? So you get a really nice correlation. And there's one point that actually deviates a little bit from that relationship, and there's that black point at the bottom, where you get, again, about the factor 3, factor 4 in extra pressure loss. And that's one of those conventional vibrated concretes where we started at an initial slump of 7 inches, and it reduced just due to the pumping operations and due to time and due to temperature, it reduced to 2-inch slump. So for the low slump mixtures, increasing slump is really going to be helpful. because you see this one point was the opposite. It had a low slump, and it is significantly higher than the remaining correlation we have for all the other mixtures. But on the other hand, anything else, it really fits the line. So viscosity is really a good thing to reduce, and viscosity is what dominates the pumping process, especially for the fluid concrete. And it's normal because for any other material, viscosity dominates any flow parameters through a pipe. So how can we reduce viscosity? And I'm just going to discuss a couple of options. I'm not going to discuss them all. But what you see here is the effect of paste volume and how we can reduce pumping pressure. And again, you get the raw data here, which is pressure versus flow rate. And the dashed lines are our non-SCC or close to SCC mixtures, highly workable concrete. And the full lines are the SCC, the self-consolidating mixtures. And then any green curve have a paste volume of 35% by volume. And the black line has a paste volume of 37.5% by volume. And the red line is a 40% paste volume. Now, what you see is a clear effect. If I increase paste volume, there's definitely a way I can reduce pumping pressure, right? And it's going down more spectacularly than our slump flow. But the big one is the water to cement ratio. You know, Walt, when you told me you work with a water cement ratio of 0.22, well, we got the curve here as well, right? If I increase the water cement ratio from 0.22 to 0.34, I reduce pumping pressure by about a factor 10. It's huge. And the big jump is really made going from 0.25 to 0.22. So if you're already low and need to go lower, it really is going to hurt, right? So that's what we see over here is that our water cement ratio is crucial for those high strength mixtures. So how to reduce pumping pressure? Well, you want to increase the water cement ratio, but you're all telling me right now that's not possible, and I agree. Because a concrete producer is not just going to make a concrete with a low enough water cement ratio to annoy the contractor. No, concrete producer is going to make a low water cement ratio because they need to make strength, and usually going to try to be as high as possible. So you can't really increase the water to cement ratio. Increasing the paste volume, it will give you a more limited effect. It's not as spectacular as the water to cement ratio. But then you get more risk for mixtures that need high modulus, mixtures that need to reduce creep and shrinkage. Increasing the paste volume is contradictory. It's not really going to help with this. So we get another constraint, a structural hardened material property constraint on trying to decrease our pumping pressure, right? We tried to change the binder system, but we really had some issues with the mixture that only contained fly ash. So not really any conclusion on that from our side. And we changed a little bit with the aggregate range of distribution, nothing spectacular. And just pumping pressure wise itself, we didn't really see significant difference. And we did not see any issues with segregation either. But again, we did not play with major variations in the aggregate range of distribution. Now I got one more parameter, and that's the pipe radius. What about that pipe radius? How is that going to play? Or the pipe diameter, how is that going to play? Right? And what we did is actually look, based on all the rheology and interface rheology we had, and plug it into the equation and see what our pressure loss would be when we do a 4-inch and a 5-inch diameter pipe. So just theoretically, this is the relationship between the pressure loss in the 4-inch pipe relative to the pressure loss in the 5-inch pipe. And there is some variation because of the influence of rheology. There's some variation because of the influence of the yield stress. As you see that the darker points, these conventional vibrated concrete points are a little lower. But what we generally see is that if I reduce my pipe diameter from 5 to 4 inches, we increase pressure loss by a factor 2. A factor 2, right? There's not that many factors that really are helping us with a factor 2. And then you're wondering, did this happen in reality? I mean, you have a little more scatter on the data. There's probably something else that plays a role as well. But we still get that factor 2. It's even a little higher, right? So increasing pipe diameter could actually be a very viable solution if you're running into issues with your pumping pressure. It is really helpful, and it's a little over what the theory would predict because of some size constraints and so on. So after the water cement ratio, we found that actually our pipe radius is the most influential factor. And to continue with the Amos kind of presentation of it, you just need a little bit extra concrete, right? And the cleaning out is going to give you a little extra concrete, but if that solves you a bunch of issues with pumpability, that could definitely be a solution. So how to reduce pressure for high strength and highly flowable concrete. What really helps, and what actually would be my recommendation, because everything else is not really possible with certain limitations, what really help is to increase the pipe radius, right? It might be your best option if you cannot change the concrete. And again, what we found going from a 4-inch to a 5-inch, reduce pressure loss and reduce the pressure by a factor 2. If we can play with the concrete mix design within the requirements of the project, right? If we can do that, then if you can reduce viscosity, that's fine. Keep your water to cement ratio as high as possible and as high as allowable, but make sure you meet all the mechanical properties. An increase in paste volume will be helpful from a pumpability point of view, but might not be helpful from a bunch of other perspectives. And from other rheological studies, we know that silica fume and fly ash are really helpful in reducing viscosity, and this could be considered really helpful in reducing pumping pressure as well. What does not really help is the high-range water-reducing agent. If the concrete is flowing well, there's not going to be a major effect. So does more super help? No, not really. Confirming what Walt Model has told in his presentation over here. With this, just want to acknowledge the sponsors of the project, which was Kamal's Industrial Chair on High Performance Concrete with Adaptive Rheology. And then we had 2 additional partners, Sodamco and Weber, who also funded part of this research. And if you got more questions, feel free. I'm here to answer, or you can send me an email. Thank you.
Thanks, Dimitri. And I encourage anybody to put a question in the chat or the Q&A. I guess I'll kick it off with a question. About the binders, you mentioned fly ash and fume. Does slag have any impact on this at all from what you've seen?
We didn't study the slag. We didn't
Okay.
look at it. If slag can reduce viscosity, it's going to be helpful. But I still need to see lots of cases where slag can spectacularly reduce viscosity. And that aspect, and I know it costs a lot more money, but silica fume was really helpful. We've seen in the rheological study we did ahead of all these pumping experiments, is that actually getting a 6% silica fume replacement actually more or less divided the viscosity by half. Now,
okay, and then another question I have for you. Is there any way that you've seen to test this in a lab without a pump?
No,
Okay.
not really. We've tried gravitational, where you got a big reservoir sitting a couple of feet higher, but we can never get to the same flow rate. We can never induce the same kind of pressure on the system that actually is going to allow us to make things flow through the system. So gravitational is not going to work just because you can't hit the amount of pressure. The only other solution I can think of without the pump is actually numerical simulations, but I don't think we're at that stage yet where numerical simulations are able to predict pumping and pumping
Okay,
rate.
thanks. Question from the group. Does T1L make any difference one way or the other?
What do you mean T1L?
Portland limestone cement.
Portland,
Type 1.
okay, Portland lime cement. And again, if the limestone filler can reduce viscosity, it can. Again, with the percentage of limestone right now in a Portland cement, I'm not sure how much reduction in viscosity you'll see. Now I need to dig into my mind. We have not tried the limestone. We have not tried that, but I'm thinking about everything we've done back in the days for my PhD, because I worked with SCC with limestone fillers. Maybe a little. And then again, whatever reduces viscosity is going to help us reducing pumping pressure. Just if I can go back in the slide here, just because of this slide. Just because of this slide. That was the big finding of this research. Well, it's nothing spectacular, but it's just the way everything fits that viscosity line. And again, if you go to a more conventional concrete, the yield stress is going to play more a role. This is going to be a little more scatter on the graph as well.
Okay. Another question. If we assume plug flow, why is viscosity of the concrete a factor?
Plug flow will only happen when the yield stress of the concrete is sufficiently high and the viscosity of the concrete is sufficiently low. From all these experiments over here, which, let me think, there's about 1,000 data points we had where we could consider, we need to look at which equation, because I only showed one equation. If I go back in the presentation, I only show one equation. There's a second equation, but all this viscosity thing doesn't really matter. Well, the viscosity of the lubrication layer will still matter, right? But there's only a couple of the 1,000 data points. It's about 1% of what we've done, including the conventional vibrated concretes that are really showing plug flow. On top of that, if your concrete is really sticky, and you have to consider that this is dominated by the flow rate. Well, it's a mix. It's dominated by pressure and flow rate, by your pumping power. If your concrete is sticky, it will prefer to shear than to flow in a plug. So again, the mixtures we pumped over here, about 1% of the data points are only in plug flow. The other 99 are showing shearing flow. I'm not saying how much, some with a low percentage of shear flow, but with shear flow. And the second thing, what really matters, even if you have plug flow, then that viscous constant of the lubrication layer is still a dominating parameter, and that one is related to the viscosity.
Okay, thanks. Another question. Would it be helpful to reduce the viscosity of the concrete without impacting yield stress to minimize possibility of segregation?
Depends on the yield stress. If the concrete is stable and heated, oh, well, now we're going on ice with this though. If the concrete is stable, right, by having enough yield stress, you could, technically speaking, reduce the viscosity. Now, on the other hand, it depends on how long the concrete is going to be in motion. Because once the concrete is in motion and is being sheared, you actually exceed the yield stress. And if you exceed the yield stress, it's no longer there to stabilize the mixture. So it will depend on how long the concrete needs to move. Now, one thing we did not observe was issues. Now, we didn't go vertical, but we did not observe issues with some of the mixtures that completely segregated. We have some really badly segregated mixtures, including the one with the fly ash. That thing still pumped pretty fine and still has very low pressure losses. But if you can reduce viscosity without affecting stability, it will be helpful for pumping.
Thanks. Those are all the questions that we have, Dimitri.
All right, great.